o'clock on Monday, September 13th, and I will pound down the September 2021 meeting, general meeting for LA Astronomical Society is hereby in session. Okay. Now, of course, where we got Tim Thompson as our speaker, because we had another speaker that couldn't make it tonight. So what I'd like to go over is Spencer, are you recording the meeting now?
Yep, it's being streamed to YouTube right now.
Okay. And then, of course, use the chat feature for any questions or comments you may have to our illustrious Tim Thompson. And of course, everybody will be muted for the time when Tim is talking, unless Tim says it's okay to have everybody talking at the same time. So we'll just go ahead and mute everybody when Tim Thompson is speaking for tonight. Okay, number one. The other thing is, throughout the meeting, you'll see Spencer will put the link for the door prize registration, so you can register for your door prizes for tonight. So Spencer will go ahead and do that throughout the meeting. Okay, the first thing on the announcements, the new members. I have two new members on my list right now, Melissa Carter and Robert Ramirez. Melissa, would you like to say something and why you decided to join this crazy crew?
Hi, everyone. Nice to meet you.
Hi, Melissa.
Hi.
Hey,
welcome.
So I'm really into science and astrology and astronomy. And I say really, I'm learning more and more about it. It's just a natural passion of mine. And so I researched and found you guys, and I look forward to learning more about the universe.
Well, you'll learn a lot tonight with Tim's talk.
Okay.
Okay, thank you. Robert, would you like to make a statement?
Sure. Thanks for allowing me to join. Took an interest the last couple of years with astronomy. Got a telescope and just need some guidance and see what you guys what you're all about.
Great.
Okay, thank you, Robert. As soon as we get everything back open again, you can bring your telescope out to Garvey Ranch and we'll be able to figure out how it works. I mean, somebody in this club should be able to figure out how a telescope works.
Nice.
Okay, do we have any other new members? Okay, it looks like we're okay on the new members. The announcements we'll talk about right this minute. Number one, the Garvey Ranch, we are opening it conditionally to members. We are not allowing the public except for anything that we may do on the grass outside. We're limiting the number of people in the observatory. Maybe Tim can go over that a little bit more, exactly what we haven't come up with an exact game plan from the board of directors yet of how we're going to handle it right now, but we'll be coming up with some game plans of what we're going to do to reopen Garvey Ranch. And it's also with Griffith Observatory the same way. We're not committed to any of the activities at Griffith Observatory yet as a club. So we need to hash this out in the board of directors exactly what we're going to do. We have some concerns that some of the board members are concerned that we may have some legal issues with the COVID. So that's why we have to basically keep everything shut down for now. And as soon as we decide on the board of directors it's okay to start opening up more, then we will do that. Okay, so we will go ahead now to the committee reports. If we could go ahead and start off with Tim, would you like to add anything as far as Griffith Observatory and Garvey Ranch? Tim?
Oh, Tim, I can't hear you.
Okay, there I am. I haven't been in touch with Mark Pine yet. Last I heard from him, Griffith didn't want to have public star parties on their lawn. They may have changed that, in which case we'll have to decide what we want to do about that for reasons that you just went over. and the observatory is open in the grounds, and even their own guy goes out and does his thing, but I don't think they want public star parties yet. As for Garvey, I just got the email today that I sent out to the board from Robert Aguirre that we could open, but he left it pretty much up to us. And I made some suggestions, but we haven't talked about it yet, so I don't know exactly what we'll do. Whether we'll allow a small limited number of people into the telescope dome or nobody into the building at all, which is an option. And we could just put telescopes out on the lawn and let people go out there. In any case, we don't want anybody in the workshop area because we're still working on cleaning it up and rearranging it. So we wouldn't let anybody in there anyway, whether we could or not, until we get it cleaned up. And that's basically where we are now, the board, and I need to talk to Vance and of course Dave Nakamoto, who's right there, about how comfortable they are with people coming into the dome, or if the telescope is even ready for them to do that just yet. We'll see. That's
Okay,
pretty much.
thank you, Tim. Okay, and then we'll go to the Lockwood Valley Committee. John O'Brien, are you there?
Haven't seen John.
Yes, I'm here.
Yes, he's right there.
So
I
we
see.
had a fairly nice dark sky night this month. About 25, 30 people showed up. The weather was pretty reasonable. Unfortunately, we had some noise pollution and light pollution from our next door neighbor, which the committee is going to try to address with our neighbor before next month, so that hopefully that doesn't happen again. No other events planned other than dark sky night coming up as scheduled on the usual night. That's
Okay,
it.
John. Thank you for the Lockwood Committee report. Ford, Joe, I will go ahead and make the Ford Committee announcement, if you don't mind on that.
Go ahead.
Okay, currently right now, we have been locked out of the observatory by the U.S. Forest Service because of the fire restrictions in the area right now. And we do not have access through the gate. So when I be going to my house tomorrow, and I may stop by the Forest Service office in Acton and see if we can get a key for that gate. So at least we have access to the observatory, not only for any activities we want to do up there, for the fact that if there's any fire restriction, any fire or anything like that, we have to get in there to get something out or something. We still need to have access to it. So I'm going to stop over at the Forest Service office tomorrow and talk to them and see if we may be able to get a key for the gate, or find out the status of the lock that we used to have on there and see if they may have it up at the Big Pine Station. So right now, as it stands, Ford is closed right now. But as David Yackerson was mentioning at the last board meeting, the forestry may have restricted the access to the forest department because they don't have staff for fire protection right now. And they're tentatively supposed to open it up on the 17th of September. But we don't know what's going to happen until, number one, until we get there. But I will see if I can talk to them tomorrow when I go up to Antelope Valley. So that's the Ford. As far as, well, it doesn't make too much difference. We've got a full moon this weekend, and next weekend we've got the third quarter moon. So depending on the forest access or accessibility to the observatory, we may not have any activities until we get back in there. Okay. Any other committee reports need to report on? I think we're okay. Spencer, we need to get the, if you could put the link for the registering for the door prizes, that would be nice.
Yeah.
And then our speaker tonight is our our good standby, Tim Thompson.
Way to
Spencer,
introduce them.
uh, Tim?
We ask about new members?
huh? We already
We
went to
ask
the new
about
members.
new members?
Yeah, we
already
did
went
that.
to the new members.
Okay, I'm sorry, I missed that. I was a little late.
So you must have been late then, Daryl, huh? Do you have
Yep, I was
anything
a
to say
little
about
late.
Mount Wilson right now, Daryl?
Under the same thing with the Forest Service until the 17th, we don't know.
Okay, well, I'm going to see if I can get an answer tomorrow from Acton and find out. Although Mount Wilson is covered by Santa Anita, so who knows?
Yeah.
But anyway, I'll see if I can get an answer tomorrow from the Forest Service. So then I think Spencer, go ahead and introduce our speaker. Although I think most of everybody on the line actually know our speaker. So Spencer, it's yours.
Okay, yeah. So this is Tim Thompson. I think Tim has been physicist and astronomer. Worked for NASA JPL for 28 years after the Air Force. Got his MS and Masters in physics from Cal State LA. He spent a lot of time in radio astronomy at JPL, and also has done a lot of work with infrared astronomy. So Tim's president of the Consortium of Western Astronomers and member of the Board of Trustees for the Mount Wilson Institute. He also serves as a docent and observing session director of the observatory. I think those of you who've gone to sessions at Mount Wilson, Tim's either been the session director or the operator. He's been president. Tim, I forgot how many times you've been president. I fudged and just put several times, but you've been president
12 times I've been elected president of the LAAS.
How many years
all?
How many years cumulative?
That's 12. Annual election.
Oh, that's right.
So,
That's
yeah.
annual. Yeah. Okay. All right. And he's currently on the board of directors. He participates in LA outreach and education events. And I love it when he gets his wizard hat and robe and has his Ask the Scientist session. And that really gets the kids interested. So the title is How Big is the Universe? And Tim, you want to take it from there?
Yeah. I'll
stop
share
sharing.
my screen if I can here. And let's do that. And then let's do
And everybody,
that. Hey.
I've put in the link for the drawing in the chat several times. So please start registering for that. Sorry, go ahead.
That looks like it worked. Well, the title of my talk is How Big is the Universe? But what I'm really going to talk about is, how big is the universe and everything in it, size and distance scales. And I keep getting this little thing I always do that says my internet connection is unstable. So, it's the typical Zoom thing. I may go in and out at some point, but and at 8:55, if you're in the mood, just kind of, run out and watch the rocket launch. They're recording this talk. You'll be able to see it again later 2 or 3 or 4 times or something. So I want to start local, but before I do, I want to show you the numbers, just things that you want to keep in your mind throughout the talk. Like, what is the speed of light? Well, you can see it's 186,082 miles per second. Astronomical unit is the standard distance measurement in the solar system. It's a stellar solar system scale, which has been defined differently by the IAU several times, but is now defined as exactly the number of meters you see there, which is just a little under 93 million miles. It's a good enough approximation. Typical solar system scale. The parsec, which was originally defined as the distance that goes along with 1 arcsecond of parallax measurement. There's a diagram that shows parallax up here, and I will come back to it. I'm going to talk about parallax again later, so don't worry about getting to it now. I'm going to do this again later. But in order to link everything back to the standard international units, SI units, parsec was redefined in 2015 as exactly 648,000 over pi astronomical units, so that it would match the current value of the astronomical unit at that time as close as they could. And so I have the calculations there. that show you that the new astronomical unit is about 300 miles longer. I mean, parsec, not astronomical unit. Sorry about that. The new parsec is about 300 miles longer than the old parsec. And that's 300 out of about 19 trillion miles. So if you think you can observe that, you're crazy. All these numbers are ridiculously precise in their decimal points because all the definitions are exact numbers with their infinite precision, and therefore you can carry as many decimals as you like. And the light year I give on the bottom, which is nearly 6 trillion miles. Parsec is the unit of distance that all professional astronomers use. None of them ever use light year. Only the general public and press releases use light year. But I'll be using them because that's what people are used to seeing. And there you see that about 3.26 parsecs or light years per parsec and 63,000 AU in a light year. These numbers, these concepts will come up again throughout your efforts to find out how big things are in the universe. You'll need to know this. I hope you memorize that slide. I'm going to be a quiz at the end of the talk. Well, so I want to start close by and just look at the Earth-Moon system. Well, the standard unit of distance, it's the mile. It's what you're used to, right? So the moon's a couple of 100,000 miles away from the Earth. The perigee is nearest distance to the Earth. Apogee is the farthest. And those numbers all change. The orbit of the moon and orbit of everything else in the solar system is constantly changing by small amounts. They're never really constant. They change around. The moon's about a quarter of the size of the Earth, much less dense. Its density matches the density of the Earth's mantle, which lends credence to the notion that the moon was created in the big thwack when something bashed into the Earth billions of years ago and spewed out all kinds of stuff that became the moon. Because mantle stuff, because it's much too dense, much not dense enough. And of course, the mile is the standard unit, 5,280 feet, or 886 foot guys like me laid head to toe. And so if you ever wonder how big a mile is, it's about 880 guys lined up. And so that's what the Earth-Moon system looks like. Here I want to just look at the orbital characteristics and dynamics. The moon's orbit is inclined to the Earth's equator, and the whole thing is tilted over compared to the sun. The Earth and the moon doesn't rotate around the Earth. The Earth and the moon rotate around the balance point, the barycenter of the Earth-Moon system, which is the balance point. It's well inside the Earth. It's like a third of the way, half the way inside the Earth between the core and the surface. And so the Earth wobbles a little bit. If you watch the Earth carefully from outside, you see it wobble as the moon went around and made it wobble. And we know from lunar laser ranging that the moon is drifting away from the Earth in about 1.5 inches per year. And in about 25 billion years, the moon and the Earth will be mutually tightly locked and staring at each other. And 25 billion years after that, the moon will come back and join the Earth, except that in 4 or 5 billion years, the sun will become a red giant, gobble up the Earth and the moon, and we won't exist anymore. So it doesn't really matter. Don't worry about it. So here is the biggest thing in the solar system is the sun. And here's one of Alan Friedman's hydrogen alpha images of the sun from 2010. It looks cool, so I don't know why I should update it to a more modern image. Here are the vital statistics on the sun: 100 times bigger than the Earth, 300,000 times more massive. You could put over 1 million Earths in it. It's big. It's a star, but it's not quite the biggest thing in the solar system because the magnetosphere of Jupiter is actually bigger than the sun. But if you're talking about a physical thing and maybe not a magnetosphere, the sun dominates the solar system in terms of mass as well as size. The big story is the bottom line here. The sun is bigger than 95% of other stars. It's constantly repeated by everyone that the sun is an average ordinary star. It's ordinary in the sense that it's a main sequence star, but it's by no means average. It's bigger than 95% of the things around. So it's big. You don't need to have an inferiority complex because you come from an average or small dwarf star. The sun is big, bigger than 95% of the stars around it, so you can relax and feel like you come from a big, meaningful star. So how big are sunspots? Well, here's another Alan Friedman image from the 2012 was a really active year in the solar cycle. We had some really big sunspot groups, and here's one of them. And you can see the Earth there by comparison. The Earth is a little bit smaller than the umbra of the sunspot groups. And these are by no means the biggest sunspot and sunspot groups around. So small sunspots can be smaller than the Earth, but sunspots can be considerably bigger than the whole Earth. And they're basically a magnetically protected bubble on the surface of the sun. You could spend a whole hour just talking about sunspots. In fact, most of the things in my talk, you could spend a whole hour on just them and not worry about the size. And so I have to kind of go through things a little bit quicker than I normally would. So this shows you how the Earth compares to sunspots, but not necessarily how big the Earth compares to the sun. I told you it was 109 times, but that's a little, what does that mean? So here is a nice demonstration. This is a solar dynamics observatory image from 2010. This, see if I can see my arrow may show up. This is a hanging prominence that runs all the way across the sun and comes around and comes back. It's about 430,000 miles long. That's about half the diameter of the sun. Now, of course, Jupiter and the Earth are not actually that close to the sun, or life would be a lot more difficult around here than it is. But those planet images are put there to show you the relative size. That's the correct relative size of Jupiter and the Earth compared to the sun. So now you know how big it really is. It's that much bigger than the Earth. It's actually very big. So we want to step out from the sun and look at the solar system. So on the upper left quadrant, looking at the inner solar system, the outer red curve is the orbit of Jupiter. And I put up there the aphelion, perihelion, and average distances. So aphelion, which is the farthest distance from the sun, is about 5.3 astronomical units, and perihelion's about 5, average about 5.2. It's not a very eccentric orbit. It's fairly round, fairly well behaved. Takes Jupiter a little less than 12 years to go around the sun once. But things get a little different when you go to the outer solar system. So when you look in the upper right quadrant, Neptune, which may or may not be the most distant planet from the sun, depending on your emotional attachment to Pluto, is a fairly circular orbit, varies from, say, 29, almost 30 to 30.3 astronomical units from the sun. Takes 165 years to go around once. But Pluto is in a much weirder orbit. It's highly inclined, and I'll demonstrate that in a few minutes. But it gets closer than the aphelion distance for Neptune. So it occasionally comes inside Neptune as far as distance from the sun is concerned. Did that some decades ago. Now Pluto is farther out than Neptune, and goes all the way out to nearly 50 astronomical units, nearly 250-year orbital period. And the Kuiper belt, which is also illustrated here, has a very sharp edge at about 50 astronomical units because of Neptune. And Pluto, along with about 600 Plutinos, are all in a 2 to 3 resonance with Neptune, which means for every 2 times orbit, Pluto goes around the solar system, Neptune goes around 3 times in lockstep. So they're never going to collide with each other. So we back out from the realm of the planets, which is what we classically thought of as the solar system. See the long, skinny red orbit is the orbit of Sedna, which shows up in the upper right quadrant as a dot outside the Kuiper belt. The orbit of Sedna is very eccentric, cometary-like orbit, goes all the way out to 937 AU. It's heading in towards perihelion now, and around 2075, 2076, it will make it 11,000-year orbit. And if we back out even farther, the Oort cloud of comets, that's kind of a spherical shell that surrounds the sun. And its real distance is very nebulous, anywhere from 10,000 to 100,000 astronomical units. So this circle shows 10,000, which is 55 light days. So at the speed of light, it takes 55 days to get out there. And anything that's 10,000 astronomical units from the sun has a 360,000 year orbit. So it takes a long time. This is what the standard solar system looks like. We get distances in the solar system using parallax, and it's worth noting that the first absolute distance measurement in the solar system was Mars. It was done by Giovanni Domenico Cassini, because he's actually Italian, not French, although he used the name Jean-Dominique, and so did his son. In 1672, he and his buddy in French Guiana both looked at Mars at the same time, figured out the parallax from the triangle, and got within 7% of the distance we use now. So they did a fairly decent job. Now, just as the Earth and Moon doesn't rotate around the Earth, but they go around the barycenter, the same thing is true for the solar system at large. The planets don't orbit the sun. The sun and the planets orbit the balance point, the center of mass, which is called the barycenter of the solar system. So this diagram, the shaded circle with a yellow dotted outline, is the sun. So any point inside that circle is inside the sun, any point outside is outside the sun. So the sun is about 99.86% of the mass of the solar system, which leaves 0.14% left over for everything else. And out of that 0.14%, 0.126% is Jupiter. And so of all the mass in the solar system, only 0.014% is not the sun or Jupiter. So really, the solar system consists of the sun, Jupiter, and a bunch of junk. And the dynamics of the system is almost entirely controlled by Jupiter. And it's mostly Jupiter that causes the barycenter of the solar system to make excursions like this. And you can see in the upper left, at this point, getting close to 2022, the barycenter is nearly a whole solar radius outside the sun. So the sun is orbiting around that point, just as Jupiter and the rest of the planets are orbiting around that point. But as the planets move, the balance point changes and it will come inside. And around 2030, you can see it's pretty close to the center of the sun. Then it will come out again, and by 2040 and 2039, it's going to be outside, and then it comes back inside. So fairly complicated excursions because of the motions of the planets. So just remember that everything in the solar system, in any stellar system, globular cluster, doesn't matter what it is, any gravitational system, going to be orbiting around that balance point, not necessarily an object. And I also just want to show the layout of the solar system kind of sideways. When you saw the plan diagram I showed before, it is flat, so you can't tell that the orbits of the planets aren't in the same plane. Most of them are pretty close, but Pluto and Mercury are fairly highly inclined. Pluto's nearly 18, well, it's 17 degrees, Mercury over 7 degrees, and then Venus at 3, and then the rest of the planets are pretty well packed in with their orbits nearly coplanar within a couple of degrees. But Pluto and Mercury stand out for their high inclinations, especially Pluto, and in its 2 to 3 orbital resonance with Neptune, that means that they can't collide because there's only 2 points where the planes of the orbits of Neptune and Pluto would cross anyway, and they're never in the same place at the same time, so don't need to worry about it. And the diagram in the upper left shows you the orientation of the planet, so you can see the N with a little arrow on it, that black line sticking out the bottom, and the connected arrow on the top show you the spin axis of the planet. That's the axis the planet is spinning around. The arrow, the big fat arrow, shows you the direction in which it's turning. A white arrow means it's prograde, it's rotating the way it's supposed to. And a blue arrow means it's retrograde, which means it's rotating backwards. So Venus barely rotates backwards. Uranus is laying down on its side and rolls around the sun like a ball. And so sometimes the North Pole is facing the sun, sometimes the South Pole is facing the sun. And Pluto is almost like Uranus laying down. But Mars, Earth, Neptune, Saturn are tilted pretty much similar. And Jupiter and Mercury and Venus are like, straight up. Now, we tend to think of the solar system as being all that stuff in close, but here we're looking at the Voyager spacecraft, which have left the magnetic environment of the sun some years ago and are now drifting in the interstellar plasma. I checked on them this afternoon at 3:30 p.m. and Voyager 1 was 154 astronomical units away from the sun, and Voyager 2, 128. The times that I put in parentheses is the one-way light travel time, which means if you send a radio command to the spacecraft, that's how long it takes for the radio signal to get from the Earth to the spacecraft. And if you want a confirmation from the spacecraft, which is standard procedure, takes that long for another signal to get back from the spacecraft. So you've got, say for Voyager 1, like 42, nearly 43 hours for you to find out whether or not the spacecraft actually didn't garble the signal and got what you expected. Then you have to do it again if it did. So you to plan things well in advance if you're going to command them to do things. They are moving at about 32 to 35,000 miles an hour. So since I checked on them this afternoon, they've moved about 160,000 miles. They are not outside the solar system, despite numerous press releases saying that they are. They're outside the magnetic boundary of the sun. But if you're talking about being gravitationally bound, they're way down deep inside the solar system. And I'll talk about that in a few minutes too. In the meantime, here's how the planets compare to each other in size. I've given you if you look at the Earth, on the top, I've given you the diameter in miles and the mass in kilograms and what the Earth would weigh if you put it on a scale, if you could figure out a way to do that. And for the other planets, the size on top is a fraction of the Earth and the mass is a fraction of the Earth. So Jupiter is about 11 Earth diameters at the equator, Saturn 9.5, Uranus and Neptune, say 4, just about 4, and so on. Venus is nearly the same size as the Earth, but Mars is half the size of the Earth for all the press that it gets. Now, the sun, we're going to go back to the sun for just a minute to remind you that the sun is a star in the universe of stars. And since I've talked about how big the planets are and distance scales in the solar system, I want to talk about the relative sizes and distance scales amongst the stars. And so this diagram, okay, you've already done the planets. This diagram, the first object in it is the last object from the previous panel. So on panel 2, the first object that's right above the number 4 is the Earth, which is the last object in the previous panel. So you can see how the planets are lined up by size this time. And so on panel 3, the first object is the last object of panel 2, which is Jupiter. So in panel 3, the first object is Jupiter. And the object next to it is Wolf 359, for all you Star Trek Next Generation fans. It's a minimal mass red dwarf star, not much bigger than Jupiter, just about the smallest mass you can get to do proton-proton fusion and actually have a real star. And the sun is the next object. And remember that the sun is bigger than 95% of the stars around. So the vast majority of stars out there are between Wolf 359 and the sun in size. Sirius, that star next to the sun, is about twice the mass of the sun and nearly twice its size. Sirius is the first object there in panel 4. Sirius is a main sequence star, so technically it's a dwarf star like all main sequence stars, despite its enormous size. And then the other stars in panel 4 are red giant stars. Pollux, Arcturus, Aldebaran, which has a little less massive than Sirius. So when the sun, in 4 billion years or so, will look like something between Arcturus and Aldebaran. It will be about that size, pretty close to the size of the orbit of the Earth in our solar system at the moment. And that's a standard red giant star late in its evolutionary phase. Over in panel 5, Aldebaran is the first object, and Rigel is the next object. And Rigel is a blue supergiant star. And the blue supergiants are much smaller than the red supergiants, but it's still about the same size as the orbit of Mercury in our solar system, and maybe 20 solar masses, and maybe 60,000 times brighter than the sun. So if you put it where the sun is, it would be enormous in the sky, many degrees across, shine 60,000 times brighter than the sun, and the best sunblock would not help you much. Next to that is Antares and Betelgeuse. Betelgeuse, devilishly hard to get the distance to Betelgeuse. So its true size is really not well known any more than its distance is, but it's about the size of the orbit of Jupiter in our own solar system. It's a pretty good bet that Betelgeuse is now known to be a little farther away than we thought it was, therefore a little bigger, and therefore about the size of the orbit of Jupiter. It's very large, obviously, for a single star. Betelgeuse is the first object in panel 6 and goes up to VY Canis Majoris, which was the largest known star when this was made, but it's already been dethroned by another star, which is approximately the same size as we thought VY Canis Majoris was, around 2,000 times the size of the sun, big enough to hold 8 billion suns, and about 10,000 times the diameter of Wolf 359. So there's a factor of 10,000 between the smallest and the very largest stars. And VY Canis Majoris is way up there. It's the biggest that you're going to find an individual star in terms of its linear size. Now I want to come back to parallax again, because parallax is the root of the parsec as a unit of distance. As this diagram illustrates what the other diagram did, that you look at a foreground star and compare it to the very far background stars. And as the Earth goes around the sun in its orbit, if you observe it, say in January and July or June, 6 months apart, you can see in the two upper panels on the right there, that star will appear to change its position relative to the stars behind it. In the same way that if you hold your finger out in front of you, the old elementary school trick, you blink your eyes, look at it with your left eye and your right eye and your left eye and your right, and watch your finger bounce back and forth in front of your face. Same thing is happening here. That's parallax caused by the baseline separation between your two eyes. And so it's simple trigonometry. So the distance in astronomical units is just 1 over the tangent of the angle that's illustrated there in the diagram. And if you want to know the distance in parsecs, it's 1 over the angle in arc second, so that 1 parsec correlates to an parallax angle of 1 arc second, which is actually very large. Nothing has a parallax angle that large outside the solar system. But since it's been newly redefined, now it's no longer linked to the parsec. It's, like I said before, it's a new definition, about 300 miles longer than the old definition. But the reason, excuse me, the reason professional astronomers have always used the parsec and never the light year is that the parsec, when it was associated with 1 arc second of parallax angle, was associated with something that you would measure. And there's always a big push to associate things with something that's measurable and objectively determinable. Now all the units have been redefined to meet the standard international unit system. And so it's not quite that way anymore. Now the Gaia mission promises to change all our understanding of parallax distances. It can do things that you can never do from the Earth. It can look as far as 30,000 light years away instead of maybe 1,000. And already the Gaia Data Release 2 has something like 1,600,000,000 objects in it that have 5 parameter fits and 1,300,000,000. It basically has 3 billion objects that it has already observed and parallaxed in some way. So it's enormous science is already coming out of the Gaia mission. It's worth a big, long talk of its own. Huge understandings, new understandings of the stars in the Milky Way. And it's discovered a few low surface brightness galaxies that we didn't know existed before, dwarf galaxies nearby. So this is the basic way of getting distances that are in fairly close. Now, I should go back and mention this. Direct trigonometric parallax is something you measure straight away. If things are too far away, you can use statistical methods, and these two, secular and statistical parallax, where you use either the proper motion of the star, which means its motion across your line of sight, or the radial motion of the star, which means the motion along your line of sight. And you use statistics to project the motion of the Earth onto that. You can get a statistical distance. It's not like doing regular parallax. It's not a real high-class distance. But these methods are available, and they will become important in a few minutes, and I will talk about those again shortly. But in the meantime, there's another trick you can play to get a distance that allows you to use the Hertzsprung-Russell diagram, which I'm showing here on the left, and the spectral classification of a star, and there's a sample classifications on the right. Now, the HR diagram is basically a measure of color, which is the same as spectral type, and brightness. And you might naively think that a star could have any color and brightness it wanted to have, but that is very much not so. And this diagram, even though it's not an equation, it's just a diagram, it's a very powerful look at stellar evolution. It is a snapshot of stellar evolution, and it's worth an hour-long talk of its own. But the method basically is that you determine the spectral class of a star by counting the spectral lines, pretty much. And that's what's plotted along the top of the Hertzsprung-Russell diagram on the left. And so I've shown a vertical white line where you pick you've determined a spectral class, and then you drop a white line down from there. The luminosity class, which is outlined by the purple curves on the HR diagram on the left, you can do a lot more fine adjustments in that, have a lot more purple curves, but this is just the rough diagram. And it's, it's 10 minutes to 8:55 for those of you who are sweating the launch. You determine the luminosity class by looking at the individual lines. How fat are they? How strong are they? How weak are they? And wherever that white line crosses the luminosity class you want, you just project another line out to the right, and you can pick off the absolute magnitude of the star. That's its true intrinsic brightness. The difference between the absolute magnitude, which is a capital M in the equation up there, and the apparent magnitude, which is the little m in the equation up there, will allow you to derive a distance, the logarithm in the distance, but in parsecs, using that formula. Excuse me, this method was invented at Mount Wilson Observatory around 1916 by Walter Adams, while he was doing spectroscopy on something else and stumbled over, hey, this is a really interesting idea. But the most powerful tool for cosmological distances, galactic distances especially, is the period luminosity relationship for Cepheid variable stars. These two plots come from Henrietta Swan Leavitt's 1912 paper. In 1908, she said she thought she saw something interesting and wanted to study it some more. In 1912, she published the real thing. She noticed, as you see from the plots, the variable star, so it gets bright and then dim and then bright and then dim. And if you look at its peak apparent magnitude and its bottom apparent magnitude, there is a correlation with the period. And in the plots, what you're seeing is the apparent magnitude plotted vertically. And on the left, it's a linear plot with the period in days plotted horizontally. And on the right, it's a logarithmic scale along the x-axis. So you're looking at the logarithm of the period in days. And of course, that gives you a straight line. If it's a logarithmic curve, an exponential gives you a straight line on a logarithmic plot. And so it's a lot easier to work with a straight line than it is with a curve. And then you can fit the line to that plot. Henrietta knew that all those stars were about the same distance away because they were in the small Magellanic Cloud. So she knew there was a relationship, but she didn't know the distance. Einar Hertzsprung figured that out in 1913 using the statistical methods I mentioned before, secular parallax and statistical parallax. So it was a soft calibration, but it was a calibration on the left. And this is the method that Harlow Shapley and Edwin Hubble used at Mount Wilson Observatory to figure out the Milky Way galaxy, figure out that there were other galaxies far away, and so on. And the 1912 paper is an interesting study in sociology of 1912. Henrietta Leavitt is the sole author of her own 1908 paper. But the 1912 paper, Edward Pickering is the sole author. There's no authorship credit given to Leavitt at all. However, the first sentence of the paper is the only sentence written by Pickering, who says everything after this sentence was written by Miss Leavitt, and then he leaves. Why her name is not on the paper, I have no clue. Maybe it was considered too important to be authored by a mere woman, and a man's name had to be on the title of the paper. It was 1912, and things were different back then. It's very strange. I don't know. I don't understand it. It's weird. And that would never happen today, but it did then. And so there's the equation that you use. As for those of you who remember your the equation for a straight line, and you diddle around with the A, B, and C coefficients, and you can move the line around using least squares methods until you find your favorite fit through the points. And then that gives you the period luminosity relationship. So then if you pick off the period from your plot, then you can go up and get the luminosity straight away. Now there are a whole bunch of different period luminosity relationships that depend on metallicity and a whole bunch of other things. For really long distances, how far away are the really distant galaxies? You have to get even logical model. The red shift, which is illustrated here, is what you actually measure. And you can see on the bottom plot, bottom chart, the spectral lines are moved in the direction of the red end of the spectrum, and they all move by exactly the same amount. Of course, in the real spectrum, there's observational noise, so you'd measure several shifts of several different lines and average them together. And the result is in this plot on the left, Hubble's law. Edwin Hubble, his original plot in 1929 covered the very corner square where it says 00. Inside those first marks where my cursor is, that was the extent of everything known in 1929. It was linear. And now we know if you extend that relationship out to 50 megaparsecs, which is about 160 million light years, it's linear still. So it's a very nice result, although 71 is probably a little too high now. I think people would favor 69, something like that. But over on the right, you see a different story. Don't worry about what they're plotting on the vertical axis. The red shift is what's plotted on the horizontal axis. And at this point, it's good to emphasize the point that you never actually measure a distance. You're always measuring something else and calculating a distance based on what you measure. When you do trigonometric parallax, the model that you use is trigonometry, and nobody's going to argue with trigonometry as a model. So it's essentially the same as measuring the distance. But everything after that, period luminosity relationship for Cepheid, if you've got that wrong, your distance is all wrong. Here, you're using a cosmological model, feeding the redshift into it and getting a distance. And if your model is wrong, your distance is wrong. You're not measuring the distance and you don't know what it really is. You only know what your model is. You know what your model says it is. And that's all you know. And if your model's wrong, your distance is wrong. And so there are three different curves on the right-hand plot. This omega m refers to the matter in the universe, and the omega lambda on the right refers to the cosmological constant, the energy of the expansion of the universe. And this is where we get the idea of an accelerating universe, where the standard candle we use is type 1a supernova. The top curve, the solid line, is the one that fits with an accelerated expansion of the universe, and the red marks, which are all your observational data, they align with the top curve, and this is where we get the idea for an accelerating expansion of the universe. Now, this shows you how the stars are laid out around us in our local stellar neighborhood. 51 Pegasi up on the upper right, around which the first extrasolar planet was discovered, 51 light years away. Sirius is only a few light years away, Denebola 36. And so this is how the stars are distributed in space around the sun. They're all within, 20, 50 billion, 50 light years, something like that. And so the nearest star to the sun, the nearest star to the Earth is the sun, of course. The nearest star to the sun is Proxima Centauri at about 4.2 light years, which is a red dwarf star, and it's orbiting the Alpha Centauri AB system, and they're only separated by about 12 to 35 astronomical units, orbit each other in an 80-year period, and way out 15,000 astronomical units. The red dwarf Proxima is orbiting them with a period of about 500,000 years. So right now, Proxima is between us and Alpha Centauri A and B, and it's going to be that way for quite a long time, because 500,000 years is what it takes to go around once. So a quarter of an orbit is going to be 120,000 years or something. So for the next tens of thousands of years, Proxima will be the closest star to the sun. Sirius, a nearby star, is only about 8 light years away, 8.6. It's about twice as massive as the sun, super hot. And of course, the little dot down on the lower left is Sirius B, the white dwarf star, discovered in 1862 by Alvin Graham Clark, purely by accident when he was testing the focus on the new telescope he built. And it was luck that the white dwarf was far enough away to see it. So, man, I didn't know there was a star there. First, he probably thought his telescope was all screwed up and he's about to go home in disgust, only to realize that there was actually a real star there. Why is my slide not advancing? Okay. So the Pleiades open cluster is about 450 light years away, 16 light years across, has around 1,000 stars in it. You look at an image like this and you see those bright stars out in front. That's the cluster hanging around out in front, and way off in the background behind it are the background stars. It's a little three-dimensional projection effect in this image. Typical open cluster. And we're looking at distances basically in the Milky Way, and there are dust clouds. There's the Pleiades cluster again on the right. The California Nebula over on the left is about 1,000 light years away, and so is the Flying Ghost Nebula, about twice as far away as the Pleiades open cluster is. So you're looking at a wall of dust and gas that's going away from us like this. So that's 500 light years away here and 1,000 here. And this is all stuff inside the Milky Way. And here's a schematic diagram that shows you the layout of the Milky Way. Of course, you can see it. It's a conspicuous dark sky object. The Milky Way is basically a bulge of stars in the middle of the galactic bulge, a disk around it. That's where the spiral arms hang out. That's where the sun hangs out, about a quarter, about halfway maybe between the edge of the galaxy and the center. 100,000 light years across is the standard answer, but that's probably a little too small. And there's a halo of globular clusters and individual very low mass stars surround the galaxy. You can see on these diagrams how it's laid out, but we can do a much better job. We can get a much more detailed look at the Milky Way in this image. This image was first released in 2008, was updated in 2013. It's built up from infrared observations from the Spitzer Space Telescope, from radio astronomy observations tracing gas and dust in the spiral arms, from numerous ground-based infrared observations. And so we now have a really good idea what the Milky Way looks like. It looks like this. And I tried to find a galaxy that looks like the Milky Way, and there it is in the upper right, UGC 1215b, 384 million light years away. We'll talk about that later too. Standard answer is that the galaxy is 100,000 light years across, but recent observations indicate probably 200,000 light years is a much better number. for the size of the Milky Way. I think it's bigger than people thought it was. It's just really hard to see the stars at the edge of the galaxy when you're buried in it instead of looking at it from the outside. Now, I showed you earlier the local neighborhood of our sun, how the stars are distributed around it. Our galaxy is in a local neighborhood of galaxies called the local group, and here it is. The Milky Way galaxy, which you can see indicated in red on the upper left, and the Andromeda galaxy on the lower right are the two dominant galaxies in the local group, easily outmass everything else. Galaxy number 3, the third largest galaxy in the local group, which is M33, and is a satellite galaxy of M31, and M33 ought to be out there somewhere. I see 32. Oh, there's 33. So the Triangulum galaxy, M33 down here, is the third largest galaxy in our local group. And it's no more than like 2%, maybe 3% of the mass of either the Milky Way or Andromeda. And so clearly the Milky Way and Andromeda dominate the local group. They're almost the same size, around 1 trillion solar masses. And in about 4 billion years, they'll smash into each other because they're in a head-on collision course now. But there's maybe 100 galaxies in this local group that spread out like this. Amongst the local group galaxies, Large Magellanic Cloud is a dwarf galaxy that orbits around the Milky Way, apparently heading in towards the Milky Way for the first time. And you can see in the image, if it shows, there is an obvious bright patch that I'm trying to outline with my cursor. So usually when you see pictures of the LMC, you just see the interior part, but there's a halo that you can see fairly clearly in this image with a fairly sharp edge that compared to the background. So these stars, all these stars are foreground stars in the Milky Way, but there's clearly a halo of some kind around the Large Magellanic Cloud that we're seeing here. It's about 160,000 light years away. So now we're getting into the hundreds of thousands and maybe millions of light years distance to the galaxies in our own local group. Now, our local group, don't think that's the right slide. This is M31. This is the Andromeda galaxy, which is nearly the same size as the Milky Way galaxy, spiral galaxy. The Milky Way, until we mapped it out much better ourselves, you'd think, yeah, it looks something like this. It is worth noting that the bright blue stars are on the leading edge of the dust clouds typical in a spiral galaxy. M32 and M110 are dwarf galaxies orbiting Andromeda, and the core of the galaxy, like the Milky Way, is 2.5 million light years to Andromeda. So now we're on the million light year scale, just typical of any galaxy cluster. They're going to be millions of light years apart. Now we go here, and what you're looking at is the Virgo supercluster. Our local group, which is a small galaxy cluster, is embedded in the Virgo supercluster, which is a collection of galaxy clusters. And the clusters you see are not randomly distributed. They're distributed along filaments. This is a close-up illustration of what's called the cosmological filaments, or the filamentary network of the universe. It's not spread out evenly. The galaxy clusters and superclusters are aligned. And here on the right, you see at about 54 million light years away, the Virgo cluster. It's the most massive member of the Virgo supercluster. And of course, it's fairly large, so this 53,800,000 light years distance is just the close, the center, say, of the cluster. And here is an image of the Virgo cluster with the conspicuous Markarian chain of galaxies up here. And you can see this, like so many pictures, they look like galaxies. You can see things that look like galaxies. It's going to be important later on too. And here they are with the cosmic, handy dandy cosmic labels to tell you what you're looking at. It would be nice if you could just point your telescope at an object and the universe would have a label floating out there to look at and tell you what it is. But unfortunately, that doesn't work. We have to do it ourselves. M87 of supermassive black hole fame is down here, and we'll take a closer look at it in a minute. M100, the big spiral galaxy in the Virgo cluster, is not in this field of view, but here's an image of it, Hubble Space Telescope image. The key project for the Hubble Space Telescope was to go out and observe Cepheid variable stars in distant galaxies, more distant than we could do from the ground, to get distances to try to nail down the local value of the Hubble constant, which is the rate of expansion of the universe. And so M100 was the first galaxy that successfully did this with. You can see in the panels on the upper right, the brightening discovered in M100. The Spitzer Space Telescope discovered several and figured out that its distance was about 16 megaparsecs, or about 52 million light years. Here's M87. It's much bigger than the Milky Way, probably about 53 million light years away, certainly much more massive than the Milky Way, and has 12,000 globular clusters. You probably can't see it in the image compressed by zoom, but if you look in close to M87, there are lots and lots of really dim dots that go away as you get farther out. The population of them drops off. So you can see the globular clusters around M87 here. And while there are maybe a couple of hundred globular clusters around the Milky Way, there are 12,000 known around M87. And this galaxy, I only put its picture in here because it's one of the best galaxy pictures I've ever seen, and I like to stick it into my talks. It's 120 million light years away, and it's worth noting that over a distance of 120 million light years, look at the detail you can see in this Hubble Space Telescope images. You can see star clusters in the galaxy, despite it being 120 million light years away. And there is a whole bunch of background galaxies all over the place. There's one here, there's one here, there's one here. You can see background galaxies like this right through the main galaxy, like this. They're all over the place. When I started doing this, 60 years ago or 50 years ago, if you had one background galaxy in some old film image, you were super lucky. Now with telescopes like the HST, if you don't have a background galaxy, it's like, what's wrong? Something went wrong. But of particular interest is this object. Galaxy cluster Abell 2029 includes the giant elliptical galaxy IC 1101, which is the largest known galaxy in the universe. There's an X-ray image on the left and an optical image from the Palomar Sky Survey on the right. This galaxy, it's a giant elliptical galaxy that size is larger than the distance between the Milky Way and M31. It's about 2.8 million light years across, where it's about 2.5 million light years between here and Andromeda. So it is truly enormous. and it's the largest galaxy that we know of. So if you want to know how big a single galaxy can get, about 2.8 million light years appears to be it. The hard core of the galaxy is 420,000 light years across, which is still significantly bigger than the Milky Way. But its halo is considerably larger than that. So now we leave the individual galaxies kind of behind. Now we're looking at the local superclusters. I showed you a diagram of the Virgo supercluster earlier. Now we're looking at the supercluster spread out around the universe. And indicated here is the shadow. It's about 650 million light years away and 100 million light years across. Different sources give different numbers. How many galaxy clusters make up the supercluster? Who knows? 44 to 122 is the number I got from someplace. Maybe 5,700 galaxies, probably more. 71 million times more massive than the Milky Way. It's ridiculously massive. And our local group, and indeed most of the Virgo supercluster, is actually moving towards the Shapley supercluster at 820,000 miles an hour relative velocity, primarily because the Shapley supercluster is the most massive local universe object, if you want to call 650 million light years local. Its gravitational influence is enough to pull us towards it from that distance away. That's really big. Another interesting object is what's called the CFA2 Great Wall, named for the Center for Astrophysics at Harvard-Smithsonian, discovered in 1989. It's that long filamentary structure that my arrow is pointing towards. So you see this vertical long structure here. That's what we're talking about. And it's about 500 million light years long and around 300 million light years broad. That's along our line of sight. It stretches for about 300 million light years. It's enormous. And another large structure is the Hercules Corona Borealis Great Wall, which is this feature up here that is about 10 billion light years away and 10 billion light years across. So it spans about 11% of the observable universe in angular size. And it's the largest known structure in the universe, is this Hercules Corona Borealis Great Wall, which is a collection of galaxy superclusters. Now, I mentioned this before, and I want to mention it again, that this is center of the Shapley supercluster, 650 million light years away. And if you look at this image carefully, it's a Hubble Space Telescope image, you can see a lot of detail and structure. You can actually see, like in the galaxy up on the top, you can see spiral arm structure. You can see maybe some dust lane. Here you can see the difference between the core of the galaxy and the disk. 650 million light years away, you can see a lot of detail. So there's a reason for that. And when I get around to telling you how big the universe is, I'm going to explain what that reason is. But it's interesting to me that over such a long distance, you can see that kind of fine detail when you wouldn't naturally expect to. So this is the deepest, most distant image, excuse me, that we've ever made. This is the Hubble Extreme Deep Field. Hubble Space Telescope made a deep field. Then it made an ultra deep field, and then it made an extreme deep field. If they decide to make another deep field, they're going to run out of adjectives. They're going to have a hyper deep field or a super duper extreme deep field, and what they're going to call it, because they're running out of words. But the limiting magnitude here, for those of you who are into photometry, is 31st magnitude, which is pretty good, over 7 billion times dimmer than what you can see with your naked eye. The image is the size of a quarter, held up 143 feet away, which is not much. 5,500 galaxies in this image and 1 or 2 stars. This image was made by combining a whole bunch of individual observations with the Hubble Ultra Deep Field 2012. If you combine all of the exposure times required and then map this out over the entire sky, because it's a very tiny field of view, it implies 177 billion and change galaxies visible to the Hubble Space Telescope if you did this over the whole sky, but it would take you over 13,000, nearly 14,000 years of exposure time to actually do it. So I think this is not likely to happen anytime soon. But if anybody asks you how many galaxies are there in the universe, 177 billion is a good starting guess that the Hubble Space Telescope could see. And there's probably undoubtedly more that it couldn't see. Who knows how many more. Now we're going to get down to the brass tacks of how big is the universe. The first thing I want to point out is that there are galaxies in this image, like the others, that look like galaxies. And those are the kind of pictures we like to show. They're the kind of pictures you always see in talks like this. But if you look at the little panels up on top, those are the kind of galaxies that cosmologists study. They're splotches, they're 2 or 3 pixels, they're little things that don't look like anything at all, and you would completely miss them if you didn't pay attention to their spectrum and realize they were galaxies. That's what cosmologists look like. Now remember that the redshift is what you measure. It's here. And you never measure the distance. You derive the distance from a model. And that when you go over very large distances, the models give you remarkably different distances. So it no longer works to say this is the distance to a galaxy. You have to specify which distance you're talking about. So in the top group of numbers, the top bins, I give you the redshift 8.6, 8.8, 9.5, 11.9, and distances 13 billion light years roughly. Now remember, the universe is about 14 billion years old. That distance is what's called the light travel time distance. And that's how long it took the light to get from there to you. And this is the distance you will see in literally every source you ever look at, every book, every newspaper article, every sky and telescope, every NASA webpage, every news, everything you see is going to give you a distance that is the light travel time distance, and it is wrong. It is not the distance to the object. It's never the distance to the object. It's not a unit of distance, and it drives me nuts that everybody uses it as a unit of distance. It is a unit of time. It's the time it took the light to get from there to you. So for a redshift of 11.9, it takes the light 13,268,000,000 years to travel from that galaxy to you. It's not a unit of distance, it's a unit of time. And the point is that over those 13 billion years, remember the universe is 14 billion years old, the universe has done a lot of expanding. So as the light is trundling through the universe is expanding, and the thing is getting farther away. And by the time you see it, this just gives you a pseudo distance, not a real distance. Suppose that right now you could throw a switch and instantly stop the expansion of the universe, pick up your yardstick and walk from here to there, lay down your yardstick and count off the distance to that object, aside from the fact that it would take you an extraordinarily long time to do that, and you need to pack an extra lunch or something because it's a long way. The distance that you would pace off is the distance you see in that second block of numbers, from 30 to 32 billion light years. That's the actual distance, the way your mind thinks of a distance. That's the number of light year long rulers that you could lay down and mark off the distance. It's called the co-moving distance. That's the real distance. Now, there's another way you can get a distance. If you know how big something really is, and you can guess from galaxy types and compared to recent galaxies, roughly how big something is, and you measure its angular size. If you know its physical size and its angular size, you can get a distance. And that's what's called the angular size distance. And that's the distance that's in the third block of numbers. And you'll notice that it is really small compared to the other distances. And that's because the curvature of space in the universe seriously magnifies the things you're looking at. And that's why you can look over fine detail, because the universe is magnifying these things for you. And if it didn't do that, then things would not look as good as they do. And finally, you can get a distance by looking at the brightness. If you know the true brightness of something, just like the spectroscopic parallax method, if you know the absolute magnitude and the apparent magnitude, then you can derive a distance from that. And exactly the same way here too. If you know how bright something really is, compare that to its apparent brightness and you get a distance. If you do that for high redshift galaxies like 8 to 11, you get the distance that's in the bottom block of numbers, from like 300 to 400 billion light years, way larger than the light travel time distance, way larger than the co-moving distance. And that's because the light is dimming. It's an inverse squared relationship, and exactly what it is about the universe. I don't think it's the curvature, because the curvature spreads out and magnifies the object. And you'd think it would make things brighter, but it evidently doesn't. And so when you look at distances, for instance, that come out of the LIGO gravitational wave experiment, those are always luminosity distances. And for a billion light years or less, you're not really going to notice the difference. But when you get out to redshifts this big, you do. And finally, I want to make the note of the difference between proper distance and co-moving distance. Co-moving distance, you use a ruler that is fixed in size and does not expand with the universe. Proper distance, you use a ruler that expands with the universe. So the proper distance between two objects in the universe never changes. It's an invariant over the history of the universe. And we have cleverly defined our co-moving distances and proper distances so that they are at this time exactly the same. So the proper distance between ourselves and that 11.9 redshift galaxy has been 32,727,000,000 light years throughout the entire history of the universe. And there's no sign of expansion. The other distances change because of the expansion of the universe. That one does not, because the ruler expands with the universe. These are not all independent, as you can see from the formulas on the bottom, where Z is the redshift. If you know one, you can calculate all of the others. So that's very convenient, fortunately. So now we've armed ourselves with what we need to know to figure out how large actually is the universe. And once again, my slide is not progressing. Now, there we go. So the co-moving distance, using your ruler and walking off the distance just like you did before, to the cosmic microwave background is about 45,700,000,000 light years. If you go all the way to the bang, it's about 46,900,000,000 light years. And so the diameter of the observable universe is twice that, or roughly 93,200,000,000 light years. That's how big the universe is in a real sense of real distance, where you'd lay down rulers and count them off and measure the distance. It's about 93 billion light years across. And I have calculated the volume, just for grins, at 2.24 million trillion cubic light years. And I changed that into cubic miles as well. And as you can see, that exponent 10 to the 70 is so big that it's like, I don't know how many trillion. You'd have to say trillion like 5 or 6 times or something to get up there. 4.5 times 10 to the 70th cubic miles, which is just a ridiculously huge number. And you can see why we don't use miles to describe these distances, because the numbers get so big, nobody wants to play around with them anyway. And underneath here, of course, is my one slide fits all explanation for cosmology and the history of the universe, which is worth an hour talk all of its own. But I've already talked way too long anyway. So I just want to point out that while we've explored an enormous universe, 10 to the 70th cubic miles of the universe, you are here. And to be blunt, in all those 10 to the 70th cubic miles of the universe, there is only one place like this that we know about. And so, there's no place like home. And no, be nice to it, because it's the only one you've got. And with that, I'm all done. Thank you.
That is
You can
awesome
unmute
job,
yourself.
Tim. Bravo.
Thank you.
Bravo.
Yeah.
Wow.
Good
Oh,
talk,
boy.
Tim.
Great job, Tim.
Oh, boy.
No place like home.
Okay, Spencer,
Sure.
you got questions on the chat room?
Yeah, let me scroll up to the chat. First of all, I just posted the link for the drawing. So there's a chat from Elizabeth Wong. Tim, do all these superclusters connect via this filament? In other words, is it a single filament structure that winds through all the superclusters? What is this filament?
Let me.
This is
My
referring to
slide
that
darn
great
advanced.
wall that you were talking about, I believe.
Yeah, see, this kind of thing. Yeah. So what you're seeing is like this
Yeah.
CFA2 Great Wall is one filament. Here's another filament. The filaments interconnect. This filament crosses that filament, and these filaments cross this filament. This is not the whole universe. You can expand this and get even more filamentary stuff. This filament comes in and meets with this filament. So it's almost like a confused mess of strings, and there are voids in between them. And this is a result of gravity collapsing material into initially actually into the strands and the filaments, and then the filaments break up to form the superclusters. And so these filaments are like super clusters, and then the superclusters are made up of clusters, and the clusters are made out of galaxies and maybe smaller subclusters.
So those
And-
are just stars and gas and matter, just all forming the filaments.
Yeah, well, they're galaxies. Yeah,
The
and so inside the galaxies, and so the superclusters are clusters of galaxies, and the galaxies, of course, are clusters of stars and gas and dust. In the bottom of the pit is the stars and the gas and dust they're made out of, but then the hierarchy goes up into galaxies and clusters of galaxies and superclusters of galaxies and filamentary structures, superclusters of superclusters, and so on.
Okay. It's another question from Dave Yackerson. So, Tim, supposedly, will the James Webb Telescope go beyond 13 billion years if it ever gets off the ground?
I like the part about if it ever gets off the ground. It's supposed to be getting off the ground for the last 20 years or so. It's scheduled to launch on December 18th, last I heard. So we'll see if that goes. The James Webb Space Telescope claims, their telescope doesn't, but the people who use it, claim that they will be able to see the very first galaxies forming. So in terms of look back time, since the universe formed about 14 billion years ago, and we can already see a good 13.5 billion years back with the Hubble Space Telescope, there's just that little realm Hubble hasn't got to yet. And if they don't hurry up and launch James Webb, it's quite likely that Hubble will get there before them, despite being very much smaller, just because they wait so long to launch, somebody else is going to scoop them. But Hubble is small enough that maybe they won't be able to do that. And Hubble can't look at a long enough infrared wavelength. The James Webb Space Telescope will look out to, I think, 25 microns, roughly 26 maybe. And you need to be able to look into a wavelength that large to catch the really high redshift. Because we were looking in that diagram, we were looking at redshift 11.9 galaxies, remember? and seeing light travel time distances 13,200,000,000 years, there's only 800 million years, maybe 500 million years between that and the beginning of the universe and say the cosmic microwave background. But the redshift of the cosmic microwave background is approximately 1100. So there's a huge redshift space between 11 and 1100 in which those first galaxies are hiding. You need long wavelengths to get at it. So James is able to do that. They claim they will be able to do it. We will see. It's like I like to say, I'll believe it when I see it.
Okay. I think that's all the questions that are in the chat. So
anybody else have any questions?
Yes, I do, actually.
Oh boy.
Tim, it was a fantastic talk. You always come up with great talks. I was just wondering, all these quasi three-dimensional cylinders that shows all these galaxy clusters, star clusters, the local star group and local, can you publish a link so we can go to them and actually take a look at these a little bit easier? Because I'm looking on my iPad and all I see is a bunch of blurs, and it's not the galaxies as a blur, it's the text that's on the thing. It's so small. It'd be kind of neat to get a larger rendition of these 3D maps you've got.
Yeah, I'm sure I've got that somewhere because they're Wikimedia images, so that should not be difficult. I can do that.
Oh, there's another question.
Yes, you would. That would be. I think that would be a fantastic thing to do. So, is there any other questions? Anybody wants to pose any other questions?
Nasser posted one. Said you mentioned it's very difficult to accurately measure distance to the star Betelgeuse. Why is that? What about other bright stars?
Yeah, Betelgeuse is a particular problem because, and now I'll make you all dizzy by going back to Betelgeuse. Went too far. So Betelgeuse down here is enormous, and it's also fairly close, like 700 light years, something like that. Its angular diameter is about 10 times larger than its parallax angle, but it is far. So it does not have a consistent shape, and you need to find a centroid for the star from its shape, and since it's variable, that will change. And you're not really sure where the edge of the star is anyway, because the photosphere is kind of blurred in circumstellar dust and the like. And since its physical size is so much larger than its parallax angle, the uncertainty in the size induces an uncertainty in the parallax angle. So it's really hard to get a distance to Betelgeuse, primarily because it's too close. If it was really far away and didn't look like a disk, but just looked like a real point and was smaller than its parallax angle, then you'd have no problem getting the distance. But it's because it's so big that it's so hard to get the uncertainty in the parallax angle down to an acceptable level. And that's why it's hard to get the distance to Betelgeuse. And I see somebody.
Is parallax method is the only way to measure the distance
Go
to
ahead.
stars?
Well, the parallax method is the only way to do it for close stars. It doesn't work, of course, for very distant stars. It's certainly the most reliable way. You can, if you know the brightness of Betelgeuse, you could do spectroscopic parallax, but that's got uncertainties in it too, because it's a variable star. And so the things you're trying to pin down the distance with are varying all the time in the spectrum. So it's just that star is a particular problem.
Tim, there's another question about this extreme deep field picture that you showed. I mean, it looks pretty colorful. Is that colors comes from the Doppler shift and the color represents the distance?
I'm not sure which plot you were talking about.
I'm talking about the extreme deep field view of the galaxy. Hubble extreme deep field.
Oh, the extreme deep field. Yeah. Okay, I see. Yeah, those colors are for the most part pseudo fake.
Oh, okay.
If you look at the extreme deep field, yeah. So this is a combination of visible with infrared and ultraviolet data. So the visible data, like this image, is probably mostly visible light, and the colors are, the Hubble palette, but they're sort of real. But in this image, you're combining infrared and ultraviolet, and they are invisible. So you make up a color for them because you can't see them.
Okay.
So that's why the colors look the way they do.
So one more question in the chat. Can you talk about dark
I can see that Kenji Arai has a hand up. Yeah. Can I talk about dark energy?
Yeah, dark energy and how it figures in determining those
certainly
far away galaxies, or does it?
I can talk about dark energy. I can talk a lot about dark energy, but I don't know what it is, and neither does anybody else. Dark energy is the code word we assign to whatever it is that's causing the universe to accelerate in its expansion. So when you write down Einstein's field equations for general relativity, you can write them down in a way so that you have space-time geometry equals mass and energy. Trust me, you can do it. So why is the expansion of the universe accelerating? It could be geometry, and that's the way it appears, or it could be something over in the energy matter business. Nobody really knows. So there's lots of groups working on lots of ways to figure out what it actually is, because we've attached a word to it, a name. It's like giving your name a cat. My cat's name is Don, right? Well, okay, that doesn't tell you much about your cat. It just, in the same way, dark energy doesn't tell you anything about what it is you're looking for or looking at. The effect that we see is that, according to our model from the data that we've taken, the expansion of the universe appears to be accelerating. But it's always important to remember we don't know any of that. We don't know that the universe's expansion is accelerating. We don't even know that the universe is expanding. What we know is that we have a model for an expanding universe, and our model fits the data. They are mutually consistent. So if the universe is expanding, that works. But there could be something we haven't even thought about yet that explains it. We'll just get rid of the expansion altogether. Likewise, the expansion accelerating, again, we have a model, and the model and the data work really well together. So something is causing it to happen. I have no idea what that something is, but we gave it a name. And at the moment, judging from our models, it looks like what Einstein called the cosmological constant, which is a constant all over the universe, is responsible for doing it. But if you want to go to the mass energy side of Einstein's equations, now you can diddle things and make one part of the universe expand faster than another part, or make it expand and contract and do all kinds of interesting things. Who knows? That may be the way it is. So yeah, I can talk about dark energy, but I don't know that I can say a whole lot about it that's incredibly intelligent.
Kenji had his hand
Yeah.
up. Kenji?
Hi, thank you, Spencer. Tim.
Yeah.
Why do the edges of so many of the galaxies have blue stars, particularly the spirals? Is that due to dust blocking the shorter wavelengths in the denser areas, or is there more star formation at
No,
the edges
that's,
due to the presence
yeah,
of colder gases?
They're
I
hotter.
know
I think
what
they're-
you mean.
I think they're
And
hotter.
in fact, the image M31, this is probably the best image of what you're talking about this. And
Yes.
that's because this is where star formation is taking place. Whenever you see the bright blue stars, that tells you that you're seeing active star formation. When you see the yellow stars like this in the core of M31, means there's little or no active star formation. These stars are low mass and old. These blue stars are relatively high mass and much younger. And you see them out here all the way around because that's where star formation is happening in the galaxy. And as you get inside, there's little star formation going on. The Milky Way is much like that. And in images of star clouds in the Milky Way, you can clearly see the difference between the yellow and blue stars in our own galaxy that are segregated in exactly the same way. That answer your question?
Yes, but then when we look at closer nebula, like Pleiades or Orion Nebula, and we see star formation there, that's much closer still, isn't it?
Oh, yes. Now, here's the Pleiades, for instance, and now we're buried deeply inside our own galaxy. We are out in the spiral arms where there's more star formation. So the Pleiades open cluster is about 100 million years old, relatively young for stars. So they formed not that long ago. And so this was an active star formation area. And now the parent dust cloud has blown away. And we're just looking at the stars hanging around left over in their cluster, but they're very young stars. Our neighborhood of the galaxy is one of more active star formation, whereas if you go in closer to the center of the galaxy, that goes away.
Wow.
Is that due? Yes, that's for sure. Thank you. Is that due to the more towards the center just having hotter gas?
No, it has less gas. It's basically used it up. And so when we look at some high redshift galaxies, we see evidence of significant star formation. And in some other galaxies, we see very little evidence of star formation. They're called red and dead galaxies because they're too red. You need blue from the young stars.
Okay, thank you.
Another one from Elizabeth is the universe expanding uniformly.
Apparently, the universe is expanding uniformly. We, of course, only really know what's happening around us. And yes, the expansion is uniform around us. Gravitational bound structures like galaxy clusters do not expand. This is the force that this dark energy we're talking about that appears to be the cause of the accelerated expansion is not strong enough. Gravity overwhelms it. So our local group of galaxies will not cosmologically expand, but the stuff around us probably will. And there may come a time in the far distant future when the entire universe will consist of nothing but our local group, and nobody will know or remember that there was another universe out there, full of Virgo clusters and all that stuff. It's hard to say at what point the bound structures like superclusters and filaments in the long run will not.
Okay, let's see. I just posted the link for door prizes there. So go ahead and register if you haven't. Let's see. I think there was one more comment. I think, let's see. Phil, you had mentioned something about we're only 0.04% through the stelliferous era. And so Elizabeth says, what's a stelliferous era?
I'm not sure I'm familiar with that phrase. Probably refers to star formation.
Yeah.
And a universe dominated by stars. So what you might be looking at is there was a paper written long ago by Freeman Dyson on the long-term evolution of the universe as it expands and expands, expands. And Adams and McLaughlin a few years back followed that up. And so our sun will last for about 10 billion years altogether, and that'll become a planetary nebula and feed the rest of the universe with its guts and our guts, because you'll swallow up the Earth. But a red dwarf star like Wolf 359, and especially one that is, I think, low in metallicity, I don't remember the metallicity effect, can last anywhere from 10 to 100 trillion years before it does that. But eventually, after about 100 trillion years, after the formation of last red dwarf star, it will have kind of settled down and become it won't even become planetary nebula. They're just too small. They'll just settle down and become dark and cold. And then you won't have any active stars burning anymore. And Freeman Dyson calculated the extraordinarily ridiculous number of 10 to the, I think it was 10 to the 10 to the 70th power years is the time scale for all matter in the universe to spontaneously collapse into black holes because of quantum mechanical effects. And by which time the universe will be nothing but black holes, I guess, trading, hawking radiation with each other. Assuming that ever happens. We're speculating here.
Okay, that's everything in the chat. Anybody else have any questions? They want to just go ahead and open up your, unmute yourselves and just post them to Tim.
Tim, thank you so much. It's so wonderful to have you giving these lectures to us. It's like it's really special. Thank you so much.
Well, thank you. So did everybody get up and leave and watch this?
Yes, they did. Probably not. I got a good video of it though. I did. It's like for 4 minutes.
That is unbelievable.
It was very cool.
Okay, so so I think last call for registering for the drawing, then I'm gonna close it out. So give you the 30 seconds. I'll close out the drawing. So go ahead and register. And you want Alicia? You want to?
Is Alicia, is she
She with
here
us?
tonight?
I
Is
didn't
Alicia
see her.
here?
I
I
didn't see
saw
her.
her early. I
Are
saw
you
her
there?
early.
She's here.
I'm there.
Oh, good.
I'm
Oh,
there.
you are, okay.
Our vice president. Yay.
Yeah, she's here.
Hi.
Okay, good.
Hi, Elizabeth. Oh.
Hey, girl.
Okay. So,
Okay. So give me a second to collect all the information.
Okay.
So
Hopefully I didn't completely snow everybody.
No, it's amazing, Tim. Always amazing to listen to you.
And we
Great
believed
chat.
it. We
Great
believed
talk,
it all.
Ken.
We believed all of it.
Daryl.
we can't figure out, we can't figure out what you made up and what was true.
That's the whole point. You're not supposed to be able to figure out what I made up. Graduate school is all about long words. They teach you long words and you sling them together and everybody walks away thinking, wow, that guy's a genius.
I'm still trying to figure out the billions, where the billions start on your numbers.
Tim, you did a fantastic job for us again. Do appreciate that.
Definitely.
Thank you.
Definitely.
Spencer, are we okay
All
on
right,
the door prizes?
we're okay on the door prizes. Hang on, let me just
Okay,
share a
great.
screen here. So I've got a spreadsheet, a blank spreadsheet that I'm going to be posting up here.
No hat.
You guys see the blank spreadsheet?
Got a lot of names on it.
Whoops, wrong one. That was last time's. Okay, hang on. Let me just kill that one. Okay, let's see. Oops, let me go here. Shoot. Okay, let me try this one more
I'll
time.
take the hat if you win it, Carol. I'll take the hat.
Oh, you're not gonna wear a hat.
Okay. All right, are you seeing now more or less a blank spreadsheet?
Now it's
All right.
Okay.
That's it.
We got
All
it.
right. Okay, I'm gonna post names in here, and the first winner will pop up here. Okay, Thomas Hendricks.
Okay. Thomas Hendricks won a $25 Amazon gift card.
Yay.
Okay, next. Let's see. Let's delete this one. And Paul.
Paul won an LAS hat.
Okay.
Yay.
Tim Thompson.
All
Oh,
right, Tim. Whoa.
Oh, boy. Peter.
Maybe get
Let's
another
give
hat.
him a yardstick, maybe.
Oh!
Hi, I have a tape measure. Yeah.
Oh, my God.
Do what?
You want a tape? You want a yardstick, Tim?
Oh, boy. I can use one.
Okay.
He won a red flashlight. I know he's picky about stuff.
Well, that's good because I lost my other red flashlight, so I actually need one.
Okay. Cool.
All right. So next one is Annie.
Okay.
Annie won one item from the website.
Nice, nice.
All right, Annie. Annie Gross.
Hey,
boy.
thank you.
Yeah. Good.
Okay. Luis.
Luis won a $25 Amazon gift card.
The gift
Oh,
card.
go back up. Okay, got it.
Oh, you got it? Okay.
Mm-hmm.
All right. Curtis.
Yeah.
Oh, man.
I know it's rigged.
What's Carol going to get this time?
This is Curtis this time, not Carol.
No, it's me.
Yeah, but you know Carol's going to get it. Come on.
The other way around.
Curtis got a hat. Yeah.
Oh, I don't.
We'll personally deliver that.
How many hats does he own now? Wait a minute.
I know I don't have any LAS.
I still say it's rigged.
Yeah, you do now.
Oh, boy.
Okay.
Wears.
How many? Okay. How many more do we have?
3.
Okay.
Out back. All
right. Robert Ramirez,
That's funny.
New member.
one of our new members.
All right.
He won a red flashlight.
Oh, thank you
Nice.
so much.
Yay.
Thank you.
All right. Robert, you're ready for Dark Sky Night now.
There you go. Thank you.
All right. Oh, Elizabeth.
Hey, Liz.
Elizabeth.
Elizabeth won 1 item from the website.
All right.
Yay.
All right.
Good stuff there.
Yeah.
Can't hear you. You're muted.
All right.
I love LAAS, and thank you, Tim, for the great talk.
Pick something really expensive.
Okay, which I get.
You're so nice, Tim.
Bake some bread if you want something expensive.
Dave
I need-
Yackerson.
I need a
is the-
go-to telescope.
Dave Yackerson is
you.
the last one.
Hey, Dave.
Jackerson
Hey,
won a green laser.
I'll
a
take
laser.
it.
All right.
Oh,
all right.
yeah. I love green lasers.
Dave Yackerson.
I'll take it. Definitely. We need
Okay.
more. We need some more star parties though.
Can I just say at this point, I won the hat last time and I haven't received it yet.
Oh, you know what? I never got your address.
What?
Well, I'm on the member list, I guess.
Yeah, I can.
Send me your address again. I'll get it out because I replied twice, but never got a response with the address.
Okay, sure.
Is it on the roster?
I can confirm the email address. Hang on, let me. Well, okay, I'll post it in the. Okay, well, hang on. I don't have the spreadsheet open right now. Okay, so I'm sorry. What was your last name?
Born
Born. Okay, all right.
19.
Number 19.
Okay, all right. Okay, I will. Liz, Joe, I'll email you his his address from the roster.
I'll get it. I have it.
Okay.
Appreciate that. Thank you.
Go without getting a gift.
Okay. I think we're.
Are we ready
coming
to
up
adjourn?
We got 2 more, right?
Coming up on the 10 o'clock hour.
Yeah, but we got door prizes.
We weren't done. We weren't done with door prizes.
We're all done with the door prizes.
I thought we were done. Did
Sorry,
I?
Joe. You and I didn't win again.
That's all right.
Okay, guys. I think it's just about time to adjourn the meeting. And Alicia, I sent you a text earlier asking where you were because we didn't see you, and I just texted you back. I didn't
Texted
see
you.
your name on the list.
Just texted you back because I just saw my phone. I was like, oh my God.
Okay, yeah, we were kind of worried about you. That's all.
Nobody called me because I was ready to go to the meeting and then I like conked out and fell asleep and it was like nobody called me. I like did not remember. I was just gone.
Oh my God.
Okay.
That
Well,
happened to
anyway,
me
I think
too.
it's
They
time
didn't
to.
call.
I think it's time to adjourn the evening's meeting. If there's any objections to it, I will go ahead and adjourn the